P-H-Y, papa, P-H-Y, P-H-Y, papa, P-H-Y. Physics. Welcome!
Welcome to another AP Physics Camp lecture. Today we're going to be discussing free body diagrams and tension force. No, Alex, I'm not referring to the tension that moms feel when they are worried that a piñata stick is going to hit someone when it's being swung. I'm talking about the force of tension that is experienced on the piñata due to the rope being used to lift it, which is exactly what we're going to be reviewing in today's lecture. So make sure you take good notes and let's begin. First, let's start with a quick review of free body diagrams and how to calculate net force. Let's take this bear as an example. If he is standing still on this flat surface, what are the forces acting on it? You got it, Alex. The bear's force weight is pushing down on the floor, while the floor is pushing back up on the bear, which is what we refer to as normal force. Now, is there any other forces acting on it? That's right, Alex, because the bear is standing still, meaning it continues to stay at rest. That means that there is no unbalanced force present, meaning that the net force is balanced, which is exactly what would happen in this situation if we were to determine the net force of the bear. For instance, let's say that the bear's mass is 300 kilograms. What would be the force weight? Right again, Alex, the bear's force weight can be calculated based on its mass times acceleration due to gravity, which in this case would be about 3,000 newtons if we round gravity to 10 meters per second squared. So in this case, since we know that the bear is at rest, meaning the forces are balanced, what would be the normal force? Right again, Alex, the normal force would be the equal and opposite reaction to the force weight, which means it would be positive 3,000 newtons, since it is in the upward direction, and the force weight is negative 3,000 newtons, since it is in the downward direction, which means that the net force is equal to 0. Great job on the free body diagram, Alex. We would simply illustrate the focused object, which is the bear, as a square, and the forces involved would be drawn from the center of the object in the direction that the forces are acting on. This makes it much more clear to see that the forces are balanced. However, what would the free body diagram look like if the bear was standing on an incline? That's right, Alex, the force weight of the bear would still be pointing down. However, what about the normal force? You got it, Alex. The normal force would be pointing up, but not straight up. Instead, it would be upward in an angle that is perpendicular to the surface that the bear is making contact with. That's right, Alex. Perpendicular means that the normal force must intersect the surface at a 90-degree angle. And in this case, since the bear is standing on an incline, the normal force would be pointing in this direction, in which it is perpendicular to the incline. Great observation, Alex. We said that the bear stays at rest. Therefore, the forces must be balanced. You're right, Alex. The force weight is negative 3,000 newtons, as previously stated, due to its mass and gravity. However, what would be the normal force in this case? Would it also be 3,000 newtons? You got it, Alex. In order to determine what the normal force is, we need to identify the other force that is missing. And in this scenario, since we know that the bear is standing still on the incline, meaning the bear must be applying a force to stay at rest and not slide down the incline. Great job, Alex. The applied force would be up the incline. As you notice, the force weight is not on the same axis as the other two forces. So to make things easier to calculate, we would visualize an incline as if it were in the horizontal axis. In other words, the incline is the x and the normal force is the y. Thus, force weight is actually a resultant vector force of the perpendicular weight and the parallel weight. I know, Alex, it might seem like a lot, but hopefully this might help you be able to visualize it a lot better. Notice, if we were to rotate the scenario so that the surface is no longer inclined and now it is looking horizontal, we would work with less resultant vectors. Also, since we know the angle of the incline, we also know the angle of the resultant force weight vector and the perpendicular weight component. Yes, that's right, Alex. These two angles would be the same, which is the other reason we approach these problems like this, because now we can determine the two component vectors of force weight. Good question, Alex. We call it perpendicular weight because if you notice, this component is perpendicular to the surface and the parallel weight component is parallel to the surface. Yes, Alex, something like that. Basically, the perpendicular weight component would be the same as saying that it is the y component of force weight, and the parallel weight component is like saying that it's the x component of force weight. However, we often use these symbols instead of x or y because we're technically working with an incline that is not actually on the x or the y. We just rotated it to look like it to make it easier for us visually. Okay, so now that we understand these symbols and naming of the components, how would we determine what these components are? Great job, Alex. We would use the SOHCAHTOA approach to determine what these two component vectors are. And then once we know what they are, we can determine what the normal force and the applied force would be, since we know that the net force should be 0 since the bear is not moving, meaning the forces are balanced. Okay, so let's try it out. What should we do first? That's right, Alex. We must first label our triangle based on the angle given. In this case, the perpendicular weight is adjacent and the parallel weight is opposite. Okay, now that we know this, how would I solve for the parallel weight, which is opposite? You got it, Alex. Sine of theta is equal to opposite over hypotenuse, which means that we need to get rid of hypotenuse by multiplying it on both sides, resulting in hypotenuse times sine of theta, which equals opposite. Now, we just need to plug in what we know. Hypotenuse is 3,000 newtons and the angle is 20. We also know that opposite would be the parallel weight. Okay, now let's plug these values into our calculator, and you need to remember that you need to check the mode that it is set at degrees, not radians, so that you could avoid getting the wrong value. Great job, Alex. Now we can solve for the perpendicular weight by using cosine of theta, which equals adjacent over hypotenuse, which means that we need to get rid of the hypotenuse by multiplying it on both sides, resulting in hypotenuse times cosine of theta equals adjacent. Now we can plug in what we know. Hypotenuse is 3,000 newtons and the angle is 20. We also know that adjacent would be the perpendicular weight. Okay, now let's plug these values into the calculator. Great job, Alex. Now we have both the perpendicular weight component and the parallel weight component. We can determine the normal force and the applied forces with this. Great question, Alex. In order for us to do this, we need to remember that the bear is standing still, which means his net force is 0. Now, this is important because we know that the net force is consisting of both perpendicular and parallel forces, which can be written mathematically like this. Net force is 0, which equals square root of the sum of perpendicular forces squared plus the sum of parallel forces squared. That's right, Alex. The net force is basically the resultant force, which is why we use the Pythagorean theorem equation to solve for it. Now, we would need to know the sums of the perpendicular forces and the sums of the parallel forces. Remember, perpendicular forces is just another way of saying forces on the y-axis, and parallel forces is just another way of saying forces on the x-axis. That's right, Alex. The sum of perpendicular forces in this free body diagram are consisting of normal force and perpendicular weight component. Now, the sum of the parallel forces are consisting of applied force and parallel weight component. So using these three equations, let's plug in what we know. Let's start with the first equation. What do we know? You got it, Alex. Since the net force is 0, that means that the forces must be balanced, illustrating that the sum of the perpendicular forces and parallel forces are also 0. You got it, Alex. Now we know 2 out of the 3 variables from the next 2 equations, which means that we can solve for the missing variables. Let's start with normal force. If we want to solve for normal force, we would just need to subtract the perpendicular weight component from the sum of the perpendicular forces, which gives us positive 2,819 newtons as the normal force. Now, as far as the applied force, we would simply need to subtract the parallel weight component from the sum of the parallel forces, which gives us positive 1,026 newtons as the applied force. Great job, Alex. Here's another question for you. What if the bear can't continue to apply that force? What would happen to the net force? That's right, Alex. The net force would no longer be zero. Therefore, there would be unbalanced forces. But what does this mean about the bear's movement? That's right, Alex. The bear would now begin to slide down the incline, meaning there would be an acceleration. So let's say that the bear is exhausted and is no longer able to apply a force up the incline. What would be the acceleration of the bear as it slides down the incline? If there is a frictional force of 300 newtons, what should we do first? You got it, Alex. We must first calculate our new net force for this scenario. In this case, the perpendicular forces would still be zero because there isn't an acceleration on the perpendicular direction. But the parallel forces would be affected since the bear is accelerating in the parallel direction. Great job, Alex. The sum of the parallel forces would now be negative 726 newtons. And since the sum of the perpendicular forces is zero, our net force would simply be negative 726 newtons. Okay, now what? How do I determine the acceleration of the bear now? That's right, Alex. We would use Newton's second law of motion, which states that the force equals mass times acceleration. And since we're looking for acceleration, we must move mass to the other side of the equation, resulting in force divided by mass equals acceleration. You got it, Alex. The acceleration would result in negative 2.42 meters per second squared. Here's a question for you, Alex. Would the bear's acceleration be the same if this incline was made of mud? That's correct, Alex, but why? If the incline is the same and the bear's mass doesn't change, why would it be different? You got it, Alex. The frictional force experienced would be different, and we can attribute this difference to a term used in physics called coefficient of friction. Yes, Alex, coefficient of friction between the bear and the muddy incline would be different to that of the coefficient of friction between the bear and the dry incline. Basically, the coefficient of friction is a way that we measure how much friction exists between two surfaces, and we use the symbol mu to represent this value. Exactly, Alex. Since the surface of the incline changed, the coefficient of friction would be expected to change as well. Good question, Alex. Frictional force is not the same as coefficient of friction. In fact, frictional force equals coefficient of friction times the normal force experienced due to the surface that it made contact with. Let's look back at our bear scenario on the dry incline. We said that the frictional force was 300 newtons and that the normal force was 2,819 newtons, which means that if we want to find out the coefficient of friction, we would have to divide frictional force by normal force, resulting in great job, Alex. The coefficient of friction in this case would be 0.106. Notice how there's no units for it because the units for forces cancel out, leaving us with just this value. Okay, now let's say that with the muddy incline, the acceleration was greater, as you expected, and it turned out to be 3 meters per second squared. What would be the net force? Great job, Alex. It would be 900 newtons. Now, let's think, what would be the frictional force in this case if the bear still didn't apply any force? Great job, Alex. So what would be the coefficient of friction between the bear and the muddy incline? That's right, it would be 0.0446. And notice how the coefficient of frictions in these cases would be different. Okay, now that you have a great handle on free body diagrams of objects on horizontal surfaces or on inclines, and how frictional forces may vary depending on the surfaces, let's now focus on scenarios in which the objects are hanging. Okay, so let's look at this piñata, which is at equilibrium as you wait for all the little kids to line up. That's right, Alex. Equilibrium means that the forces involved with this object are all balanced, meaning the net force is zero. Thus, the piñata is not moving. Sure, Alex. Let's say your uncle is the one that's holding one end of the rope, in which the piñata is hanging from, and the other end of the rope is tied to the tree. Notice that your uncle is holding the rope at a 34-degree angle, and the other end of the rope is at a 10-degree angle. Now, what forces would be experienced on this piñata due to these ropes? You got it, Alex. The first force that should be noted is force weight, which is the force pulling down. So what forces are ensuring that the piñata doesn't fall?
You got it. The other forces that are ensuring that the piñata doesn't fall are tension forces experienced due to the ropes. Now, the question is, what would be the tension force of the rope your uncle is holding if the side of the rope that is tied to the tree had a tension force of 30 newtons? Would both tension forces be the same or different?
Great job, Alex. The ropes are being held at different angles. Therefore, they would experience different tension forces. So how about we take a look at how we could determine what tension force number 2 would be. But first, we must draw a free body diagram of this scenario. Great job on the free body diagram, Alex. Now, we know both of the angles of these ropes, which are 10 degrees and 34 degrees. So let's draw these in. We also know the side of the rope that is tied to the tree has a tension force of 30 newtons, which we're going to label as tension force number 1. Now, let's say that these tension forces are holding on to a 2.5 kilogram piñata. So what should we do first to determine tension force number 2 and the force weight of the piñata? Great job, Alex. The force weight of the piñata can be determined by multiplying its mass times acceleration due to gravity, which results in 25 newtons. But how does this help us determine tension force number 2? That's right, Alex. We know that the net force of the piñata is 0, since we stated that it is at rest. Therefore, the sum of the y forces should be 0, as well as the sum of the forces on the x-axis. Thus, we can illustrate this with the following equations, in which the net force equals the square root of the sum of the y forces squared plus the sum of the x forces squared. Now, we also know that the sum of the y forces equals all of the forces that are on the y-axis. And in this case, that would be tension number 1, y component, plus tension number 2, y component, plus the force weight. Now, we also know that all of the forces on the x-axis are going to be added up, and that's going to be the sum of the forces on the x-axis, which equals tension number 1 on the x-axis plus tension number 2 on the x-axis. Great question, Alex. Tension number 1 and tension number 2 are at an angle. Therefore, they are resultant force vectors, which means that they both have a y component and an x component. Therefore, when we determine the sum of the forces on the y-axis, we need to take into consideration tension number 1, y component, and tension number 2, y component, and force weight, because they are all on the y-axis, which is also why when we are looking at the sum of the forces on the x-axis, we need to take into account tension number 1, x component, and tension number 2, x component. Okay, having this in mind, what should we do first? That's right, Alex. We must first label our triangles, which in this case, force of y is opposite to the angle, and force of x is adjacent to the angle. Now what should we do next? You got it, Alex. We must use SO, GA, TOA to determine the missing components. Now remember that in order for us to do this, we must have at least one of the sides of the triangle. So which triangle should we start with first? Great idea, Alex. We start with tension 1 components since we know tension 1 and the angle. So based on this, we can use SO and CA to calculate the opposite and adjacent sides. That's right, Alex. We start off with the equation of sine of theta equals opposite over hypotenuse, in which we must solve for opposite by multiplying hypotenuse on both sides, resulting in hypotenuse times sine of theta equals opposite. Now we can just plug in what we know, which is 30 newtons for the hypotenuse and 10 degrees for theta. And the opposite is representing tension 1's y component, which results in 5.2 newtons. You got it, Alex. We said that the sum of the forces on the y-axis should be balanced since the piñata stays at rest, which means that the downward forces should cancel out with the upward forces. And in this case, the only downward force is force weight, which is negative 25 newtons. Now, that means that both upward forces must equal 25 newtons. And since we already know that one of the upward forces is
5.2 newtons, that means that the other must be 19.8 newtons. So what about the sum of the forces on the x-axis? How do we determine these forces? That's right, Alex. We must use cosine of theta equals adjacent over hypotenuse, in which we want to solve for adjacent to determine the tensions number 1 x component. So we must first multiply the hypotenuse on both sides, and it ends up resulting in hypotenuse times cosine of theta equals adjacent. So now we just need to plug in all our known values, and in this case we know that the hypotenuse is 30 newtons, theta is 10, and the adjacent is tension number 1 x component, which results in 29.5 newtons. So what else does this tell us based on what we know? That's right, Alex. The sum of the forces on the x would also be equal to 0 since the piñata is at rest, meaning the net force is 0 and all forces must be balanced, which means that if we only have two forces on the x-axis and these two forces are going to opposite directions, that means that they must equal the same value, which means that if tension number 1 x component is 29.5 towards the left, that would mean that tension number 2 x component must be 29.5 to the right. Great job, Alex. Now we know force weight, tension number 1, as well as its components, and we also know tension number 2's components. However, we don't know tension number 2. So how can we determine this based on our known values? That's right, Alex. We could either use so or ka since we know both opposite and adjacent, or we can use the Pythagorean theorem since we know two sides of the triangle and only missing one. Both methods would give you the same answer. So just for review purposes, let's use the Pythagorean theorem to solve for tension number 2, which is the resultant force of these two components. You got it, Alex. Now we just need to solve using these known variables, which results in 35.5 newtons. Yes, Alex, your uncle is going to probably get very tired after a while. So let's hope that he doesn't have to wait that long for all your cousins to start taking turns already. Okay, let's say that your cousins are finally ready to hit the piñata, but your first cousin decides to hit it with all their force, so your uncle decides to pick up the piñata at a constant velocity so that your cousin can't hit the piñata anymore, which means that your uncle now holds the rope at a 25-degree angle, resulting in tension number 1 to now be horizontally positioned. What would be the new tension forces for the piñata, and would the force weight change? That's right, Alex. Force weight would stay the same, but your tension forces would be different since you now have different angles. Thus, what would be your new net force? You got it, Alex. The net force would still be 0 because the piñata is moving at a constant velocity. Therefore, there is no acceleration. Thus, no net force, meaning the forces must be balanced.
This concludes our video lecture. Make sure that you took good notes, and that's it. Have a great one.